Okay, so the question I asked or proposed at the beginning of this section was, why the heck does it matter? And I told you the one that we're really going to be paying attention to is the second derivative. We won't be looking at third derivatives on up other than this section, the test for it. But those are just simple, just find the third derivative or evaluate the third derivative at a point, etc. But we will be using second derivatives for the rest of the whole next chapters. Really comes down to a significant portion of this course. So you need to be comfortable with the second derivatives. Well, why would we care about second derivatives? Well, what's the rate of change of velocity? Rate of change of velocity is called acceleration. So again, if velocity is the derivative of the position, so what's the derivative of velocity? That's acceleration. So what you really have here, what we've decided is that you have s of t is your position function, right? So then s prime of t is v of t, which is the velocity. S double prime of t, the second derivative of the position function, which is the derivative of the velocity function, is a of t, which is acceleration. Now, acceleration, in the way that we were looking at it before, the examples we were looking at before were, okay, I hold a rock above on a 180-foot building and I drop it straight down. Where's the rock at what point in time and how fast is it traveling? So all we were doing was looking at the vertical change of an object. Its acceleration is actually constant in that case. Its acceleration is due to the force of gravity. Well, gravity is measured at negative 32 feet per second, or negative 32 feet per second squared. Again, when you find a second derivative, you're doing it with respect to x again. So you are dividing by the units in the x place, or whatever those x values are, whatever that input is. So that's why you get feet per second squared. Not feet squared per second squared, just feet per second squared. Okay, so we do have our position function. Usually this is measured in feet. It's either measured in feet or sometimes you might even see it measured in meters. Your velocity function again would be feet per second, or it could be meters per second. Acceleration would be measured in feet per second squared or meters per second squared. Okay, so that's your units anytime that you have those. So just read your problem and you'll figure that one out. So let's do a nice example of this. It says a ball is thrown upward from the top of an 80-foot cliff. So your initial height is 80 feet. That's your S0 if you remember. Okay, with an initial velocity of 64 feet per second. So that means it's thrown upward because it is a positive number here. It's going up. And it says the position function is s of t equals negative 16t squared. I told you that one comes from acceleration. That one comes from gravity. Then it's v0t. If you notice here, your v0 is your 64. That's your initial velocity. And then it's always plus s0, your initial position. So remember, always your position function for an object falling without air resistance is going to be given to you by s of t equals negative 16t squared plus v naught t, your initial velocity, plus s naught, your initial position. So that's how they got that formula right there. It says where t is measured in seconds. Find the height, velocity, and acceleration of the ball 2 seconds after the ball is released. So you got to be thinking about it. This ball goes up, and then it's going to reach its peak height, and then it's going to come down. So the question is, okay, is it going up? Is it coming down? Is it changing from up to down? What's going on? So let's start off with the position function and see what we have. For the position function, that's the height. That's just s of t, right? S of t is given to us. That's negative 16t squared plus 64t plus 80. So they want to know where's it at 2 seconds. So at t equals 2, this would be s of 2, which would be negative 16 times 2 squared plus 64 times 2 plus 80. Go ahead and throw that into your calculator and see what you get. I'm getting a height of 144 feet. Again, it's measured in feet when you plug it into the initial function. So think about this. We're on an 80-foot cliff. We huck that ball upwards. This person has thrown this ball, well, it'd be, 64 feet into the air, because it started at 80 and now it's at 144. So that's a pretty dang, maybe it's not a throw, maybe that's a launch out of a cannon or something, but I don't know. Some people can throw that high for sure. Let's move on to velocity. Remember, velocity is v of t, which is the derivative of the position function. So if the position function is negative 16t squared plus 64t plus 80, then v of t would be equal to the derivative of that. Negative 16t squared would be negative 16 times 2, which is negative 32t. 64t would be plus 64 times 1. And then the derivative of 80 is 0. So I'm getting negative 32t plus 64. But remember, we need to look at this at t equals 2. So my velocity at 2 seconds would be negative 32 times 2 plus 64. Well, I'm getting 0 feet per second. So what the heck does that mean? It means the ball is no longer moving. So what have we found? We found the exact moment in time from when this ball goes from going upwards to going downwards. We found that exact perfect time where it stalls out, right? Where it stops, it's reached its maximum height, and now it's going to start moving downwards. Acceleration of t, the acceleration, we know is the second derivative of the position, or the derivative of the velocity. That's our acceleration function. So let's look at that. If our velocity is negative 32t plus 64, we find its derivative. The derivative of negative 32t is negative 32 times 1, which would be just negative 32. And the derivative of 64 is 0. So my acceleration is negative 32. So no matter at what time you plug in, the acceleration is always going to be negative 32. And again, that measure is in terms of feet per second squared. And it turns out that is the exact measure of gravity. Gravity creates an acceleration on all objects equally towards the ground. Every single object has an acceleration of negative 32 feet per second squared. So there's our answers right there: 144 feet, 0 feet per second, and negative 32 feet per second squared. Let's move on. It says in the previous example, we should notice that the acceleration of the ball is negative 32 feet per second squared at any time t. That constant acceleration is due to the gravitational force of Earth is called the acceleration due to gravity. Note that the negative value indicates that the ball is being pulled downwards towards Earth. Let's look at the next example. It says, the position function on Earth, where s is measured in meters, t is measured in seconds, v naught is the initial velocity in meters per second, and h naught is the initial height in meters, is s equals negative 4.9 t squared plus v naught t plus h0. So nothing's different there except for that leading coefficient. It used to be negative 16. Well, guess what? 16 feet is equivalent to 4.9 meters. So that's what it's coming from right there. That leading coefficient's coming from changing the units from feet to second to meters per second, or distance being feet to meters. So it says an object is thrown upwards at a velocity of 2.2 meters. So that's my v naught right there, my initial velocity. That's going to go in where we have the v naught right there. From an initial height of 3.6 meters, so that right there is my h naught, my initial height. What is the acceleration due to gravity on Earth in meters per second squared? So let's look at this original function. My original function with respect to time would be negative 4.9 t squared plus v naught, which was 2.2 t, plus h naught, which was 3.6. Well, that's our position function if we want to find the velocity. Remember, our velocity is the derivative of the position function. So we're going to do negative 4.9 times 2. Negative 4.9 times 2 is negative 9.8 t. And then it's plus 2.2t. The derivative of that would be plus 2.2 times 1. And the derivative of 3.6 is, of course, 0. That's our velocity function. Now we can find our acceleration function, which is the derivative of that. The derivative of negative 9.8t is negative 9.8. And the derivative of 2.2 is 0, so we're getting negative 9.8. But remember, our units of measures here would be negative 9.8 meters per second squared. So if we measure gravity in feet per second, it's negative 32 feet per second. If we measure it in meters, it's negative 9.8 meters per second squared.